stand on almost any old Roman bridge, the Pont du Gard in France, the Puente Romano in Merida, the Pons Fabricius right in the center of Rome, and you'll notice something. The piers have a point on the upstream side, a sharp triangular nose cutting into the current. Most people walk right past it. It blends into the stone, looks like part of the architecture, just another feature of something very old. But that little triangle is one of the primary reasons these bridges are still standing. Not for 50 years, not 100. Some of them have been absorbing floods, deflecting debris, and holding up traffic for over 2,000 years without meaningful repair. That's not an accident. That's a solved problem. The Pons Fabricius was built in 62 BC by a Roman official named Lucius Fabricius. His name is still carved into the stone today. That bridge has been crossing the Tiber for over 2,000 years. It survived the fall of the Western Roman Empire, the Ostrogoth invasions, the medieval period, the Renaissance, 2 world wars, and decades of Roman traffic and tourism. It is still in use. You can walk across it this afternoon if you happen to be in Rome. The Alcantara Bridge in Spain was completed around 106 AD under Emperor Trajan. The Puente Romano de Merida, nearly 800 meters long, has been in use since the 1st century. The Ponte di Augusto in Rimini has carried traffic since 20 AD. These are not restored replicas. They are the original structures, on their original foundations. In this video, we're going back to ancient Rome, not the emperors, not the famous battles, but the engineers. The men who stood knee-deep in cold river water, figuring out how to hold stone in place against a current that wanted to tear everything apart. Most of their names are completely lost to history. But the structures they built are still here, and the structures are the biography. Throughout this video, we'll be using AI-generated footage to reconstruct what those construction sites looked like, pulling from ancient bas-reliefs, Roman coins, and written accounts to bring scenes back to life that no camera ever captured. So, why does a triangle make a bridge that much stronger? And how did a civilization without calculators or computers arrive at a design that would outlast nearly every other structure on the planet? The answer involves fluid physics, a geological stroke of luck, and centuries of watching things break and figuring out why. Before we get to triangles, we need to understand what Roman engineers were actually up against. Rivers are not cooperative. Anyone who has tried to stand still in fast-moving water understands this on an instinctive level. Now imagine trying to build a permanent stone foundation in the middle of one, and keep it there for centuries. Roman engineers weren't just dealing with the sideways push of moving water. They were dealing with 3 separate forces, each capable of destroying a bridge on its own, each attacking from a different direction, on a different timescale. The first was something called scour, and it was probably the most dangerous of the 3 precisely because it was invisible until it was too late. Scour happens when fast-moving water erodes the riverbed around the base of a structure. As the current squeezes around a pier, it accelerates, and as it accelerates, it lifts sediment and carries it downstream. Slowly, the ground beneath the foundation disappears. The pier leans, it cracks, it falls. Scour is still one of the leading causes of bridge failure today. The U.S. Federal Highway Administration estimates it accounts for roughly 60% of flood-related bridge collapses in the 21st century, with steel reinforcement and reinforced concrete. For the Romans, working with dry stone masonry and timber, it was an existential threat on every project. The second problem was impact. During a flood, a river doesn't just carry more water, it carries everything the floodwater has ripped loose upstream. Logs, entire trees, chunks of stone masonry from collapsed upstream structures, dead livestock, broken carts, all of it moving at the speed of the flood current, and all of it heading straight for your piers. A single log at flood speed hits a flat pier face with the force of several tons concentrated at one point. The Romans couldn't calculate that, but they had watched what it did to bridges that weren't designed for it. Work teams months to build, gone in a single flood season. The third problem was the most patient: constant vibration. Water against a flat surface creates turbulence, chaotic force from every direction, year after year. That stress works into mortar joints, wiggles blocks by fractions of a millimeter. Hairline cracks form. Water gets in, freezes, expands. The crack widens. More water. Over years, the crack becomes a gap. Eventually, something moves that shouldn't. So, the Roman engineer planning a bridge faced scour eating at his foundations from below, flood debris trying to knock his piers over from upstream, and constant vibration shaking everything apart from the sides simultaneously, on every pier, for the entire life of the structure. He had stone, wood, rope, and human labor. No steel, no reinforced concrete, no testing laboratories. What he had was careful observation, accumulated experience, and the memory of every bridge that had failed before his. Before the Romans could even think about the shape of a pier, they had to solve a more fundamental problem. How do you build a stone foundation underwater? You need to dig down to stable ground and lay your first course of stone on something solid. But the riverbed doesn't stop being wet just because you want to work on it. You have to get the water out of the way first. The solution the Romans developed and refined over generations was called a cofferdam. You build a temporary watertight wall in the river around your construction area, pump the water out from inside, and you have a dry workspace in the middle of a river. Simple in principle, extraordinarily difficult in practice. The process worked like this. First, you drive rows of wooden stakes into the riverbed in a rough circle or oval around your construction footprint. You drive them as close together as the riverbed will allow, ideally close enough that the gaps between them can be sealed. Then you pack those gaps with clay, pressing it in by hand until the wall holds back the river as well as you can manage. Then you start pumping. Roman engineers used two main methods: chains of workers passing buckets hand to hand over the cofferdam wall, or Archimedes screw pumps, helical screws turned by hand that lifted water continuously over the side. Neither was fast. Neither was comfortable in cold river water, but if you kept enough workers going without stopping, you could stay ahead of the seeping water long enough to lay your foundations. In practice, it was a continuous nightmare. The clay was never perfectly watertight. Pumping could never stop. The moment workers slowed, the water came back. Shifts worked through the night, and if a section of the wall gave way suddenly, which happened, you had seconds before the whole workspace flooded. Vitruvius, the Roman engineer who wrote his De Architectura around 25 BC, describes cofferdam construction with the matter-of-fact precision of someone who has watched this go wrong many times. He discusses double-walled cofferdams for soft riverbeds and emphasizes sealing the bottom as well as the walls. These weren't theoretical suggestions. They were solutions to real failures, written down so the next engineer wouldn't have to repeat them. The Romans got very good at cofferdams. Over centuries, they refined the technique until they could reliably build dry foundations in rivers other civilizations wouldn't attempt. And once the foundation was set, the question became, what shape do you build the pier? Here is what happens when water hits a flat surface head-on. It can't stop, so it goes sideways violently, in both directions at once. That creates high pressure at the impact point, turbulent spray on both sides, and constant pounding force on the structure. Repeat that hundreds of times per second, across every flood season. For 100 years, something eventually gives. Now here is what happens when water hits a pointed surface. The water meets the point, splits cleanly into two equal streams, and flows in organized parallel lines along each side of the pier. No head-on collision, no pressure concentration, no turbulent cloud in front of the structure. The pier is still in the middle of the river, but the river has been given a path around it, and it takes that path without a fight. In modern fluid dynamics terms, the triangular cutwater reduces drag and converts turbulent flow into laminar flow, smooth and organized. Turbulent flow vibrates a structure. Laminar flow doesn't. Less vibration means mortar joints stay intact. Blocks don't move. Cracks don't form. The bridge keeps standing. There's also the question of force distribution. When water hits a flat pier face, all that hydraulic force is concentrated at a single impact point. When it hits a triangular pier, the same force spreads along both angled faces distributed across a much larger surface area. The structure takes the same total load but feels less of it at any given point. Less stress, less vibration, fewer cracks. The Romans didn't derive any of this from equations. They arrived at it through observation across generations. And one of the most consistent things they had observed was ships. Roman vessels all had pointed bows not for aesthetics, but because a flat-fronted boat fights the water while a pointed prow redirects it. Every Roman sailor and shipbuilder understood this practically, long before anyone had a word like hydrodynamics. Applying that logic to a stationary pier is a short step, once you start thinking about water as something to redirect rather than resist. The pier isn't fighting the river, it's letting the river pass. The triangular cutwater also addressed scour directly. When water hits a flat pier face, some of it dives downward and creates what engineers now call a horseshoe vortex, a spinning column of water that wraps around the pier base and drills into the riverbed. The triangular cutwater prevents the vortex from forming by splitting the flow before it can pool and spin. Water goes around the pier instead of down in front of it. And on debris, a log hitting a triangular cutwater glances off one of the angled faces and deflects to the side. The full impact force is never transmitted to the pier. Compare that to a flat face, direct hit, full force, every time. During a serious flood, when an entire hillside's worth of uprooted trees comes down the river in a single afternoon, that difference in impact handling can be the difference between a bridge that survives and one that doesn't. Other ancient civilizations built bridges: Greeks, Persians, Chinese. What set Rome apart wasn't discovering the triangle. It was the scale and the systematization. Rome built bridges the same way it built roads and aqueducts. Standardized methodology, reproduced reliably across an entire continent by different teams simultaneously. This worked because the knowledge was formalized. Vitruvius wrote it down. Engineering manuals circulated through the legions. A bridge in Britain and a bridge in Jordan, built by different people with local stone, look recognizably similar because the same logic governed both. That's institutional knowledge working as intended. The most dramatic example of Roman systematic bridge construction was military. In 55 BC, Caesar needed to cross the Rhine River to demonstrate that it was not a barrier Rome couldn't breach not to conquer, simply to appear on the other side and come back. The Rhine was roughly 400 meters wide, fast-moving, cold. Caesar had it bridged in 10 days, used it once, then ordered it torn down. Caesar describes the construction in De Bello Gallico with the calm precision of a technical report. He specifies the exact pile configuration pairs driven at opposing angles, braced against each other so the current's force tightened rather than loosened the joint. He mentions the upstream deflection barrier to intercept debris and enemy sabotage. He was thinking about hydraulic forces and impact management. He just didn't have those words yet. On permanent civilian bridges, the cutwater wasn't a rough pointed nose. On the best preserved examples, the angle is typically 60 to 90 degrees precise, consistent across every pier, carved from the same continuous blocks as the pier body, not attached as an afterthought. Integral. In some cases, the Pons Aelius in Rome, built under Hadrian around 134 AD, the cutwater extended above the waterline into the parapet wall of the bridge road, creating a wedge-shaped alcove at road level where a pedestrian could step aside to let a cart pass. The same feature protecting the foundation from the river was simultaneously solving a traffic problem on top. Two problems, one piece of stone. That kind of layered thinking ran through Roman engineering at every level. The triangular cutwater reduced the forces working against the pier. But what held the pier together under those reduced forces still had to be exceptional. And here, Rome had a geological advantage that most of the ancient world simply didn't have access to. Around the Bay of Naples, there was a particular volcanic ash from the area around a town called Puteoli, which we now call Pozzuoli. The Romans called it pozzolana. When mixed with lime and seawater, the mixture hardened underwater and continued strengthening for years afterward. The Romans discovered this empirically, probably by noticing that structures built with local ash in wet conditions outlasted everything else. They didn't understand the chemistry. They just knew it worked and started using it deliberately. Modern materials scientists have spent years studying Roman marine concrete samples from harbor walls and bridge foundations that have been underwater for 2,000 years. Researchers from UC Berkeley found that seawater had caused new mineral crystals, specifically a mineral called tobermorite, to grow inside the concrete matrix over the centuries. The concrete wasn't just resisting decay. The chemical environment of seawater was actively reinforcing it from within. This is not how modern Portland cement concrete behaves. Portland cement weakens when exposed to seawater. The chemical reactions go the wrong way. Roman engineers, working entirely from observation with no knowledge of chemistry, arrived at a concrete formulation that is in certain measurable respects superior to what we use for marine construction today. We are still working to fully understand it, put it all together. A triangular cutwater that converts turbulent flow into laminar flow, deflects debris, and prevents scour vortices. Pozzolanic concrete that hardened and strengthened underwater. Precision-cut stonework with joints too tight for freeze-thaw damage. Three things working together to produce a pier exceptionally matched to the forces it was designed to resist. The longevity isn't luck. It's what good engineering, done with the right materials, actually produces. There's a question worth asking. If this engineering was so effective, why didn't everyone adopt it permanently? For a while, within the Roman world, they did. But when the Western Roman Empire collapsed in the 5th century AD, what went with it wasn't just political authority. It was the institutional infrastructure that made systematic engineering reproducible. The state contracts, the trained corps of engineers, the technical libraries, the apprenticeship systems. When those institutions fragmented, the knowledge stopped being transmitted as a coherent system. It became localized, personal, dependent on individual craftsmen who might or might not pass it on. Medieval bridge builders weren't incompetent. They were working with fewer resources and less accumulated knowledge in smaller political contexts that couldn't fund what Rome had treated as routine. Some medieval bridges are genuinely impressive, but look at the piers. Many are rectangular or only rudimentarily pointed. And many of them failed in floods that Roman bridges on the same river survived. The contrast tells the story clearly. Recovery was gradual. Renaissance engineers in Italy, surrounded by Roman examples still standing, began studying the old bridges systematically, measuring proportions, asking what made them last. By the 17th century, European builders had re-derived most of what Rome had known. The pointed cutwater reappeared as standard practice. What's striking is how many of them arrived at the same answers independently, not by copying Roman designs, but by following the same physics. Because the physics hadn't changed, water in a 12th century river behaved exactly as it had in the 1st century. A triangle still split the current cleanly. Scour still formed vortices in front of blunt obstacles. When you look at any physical problem carefully enough for long enough, the answers stop being optional. So the next time you cross an old Roman bridge or see a photograph of one, look at the piers. Look for that pointed upstream edge. What you're looking at is the accumulated result of centuries of observation, failure, and adjustment. Engineers watching rivers, watching their own structures crack and lean and fall, asking why, and building it differently the next time. No single inventor, no singular moment of inspiration, just the slow, patient accumulation of understanding, written into stone, still standing. The triangular cutwater splits the current, deflects debris, prevents the scour vortex, and distributes hydraulic force across two faces instead of concentrating it at one point, combined with volcanic concrete that hardened and strengthened underwater, and precision masonry that left no weak joints on the exterior face. Roman bridge piers were about as well matched to their environment as the knowledge and materials of their time could make them, and the proof is simply that they're still there. Rome's engineers didn't always get it right. Plenty of their bridges failed, and the ones that failed are gone and forgotten beneath river sediment. But the ones that worked because someone had the discipline to understand the forces involved, and to put that understanding into every pier, on every bridge, across an empire that stretched from Scotland to Syria. That's the story of the triangle. Small shape, very long shadow. Dino, 45, 20, 0, seta. If this video gave you something to think about, a like and a subscribe genuinely help this channel keep making content like this, going deep into the engineering and the real human stories behind ancient history, the parts that usually get skipped over for the battles and the politics. Thanks for watching. See you in the next one.